All right, so as we mentioned last time, we're going to be starting moments of inertia, or basically this is a second area moment, and it has many applications in statics and dynamics. Um, just make a note on here. So if we're looking at an area, and I've got a picture here of an arbitrary area, we're looking for the moment of inertia about the x-axis, then that would be the distance from the x-axis, which is actually going to be y, times dA. So if here's our little dA here, our moment of inertia about the x-axis is going to use this distance y times dA. Sorry, y squared times dA, because it's the second area moment. If I'm looking for the moment of inertia about the y-axis of this little particle, then that's going to be the distance from the y-axis, which is going to be x squared times dA. So this figure also shows two other axes, x prime and y prime, and those axes go through the centroid. So we can also calculate the moment of inertia about the x, scroll over a little bit, the x prime and the y prime axis, and that's going to use the distances from the other axes. We can go between the moment about the actual x-axis and the centroid axis using the parallel axis theorem. So parallel axis theorem says the moment of inertia about the x-axis is the moment of inertia about the centroid axis plus the whole area times the distance between the x-axis and the x prime axis, which we're calling dy here, as shown in the figure, squared. So we can see that the minimum value of the moment of inertia is always going to be through the centroid. Through any other axis, it's going to be greater by the area times the distance from the centroid squared. Okay, there's a third moment that's introduced here, and that's not used as often, but it is occasionally, and that's the moment of inertia about the origin, which is called the polar moment of inertia, and it's calculated as r squared times dA, and r in this case would be the distance here from the origin to the dA. So r would be this distance. Okay, and then our parallel axis theorem, there's one for Ix, one for Iy, and one for the polar moment of inertia. So polar moment of inertia is going to be the moment of inertia about the centroid point, so about c, plus a times d squared, where d is this oblique distance from the origin to the centroid. These are going to be useful because for a lot of common shapes we have tabulated values for the moment of inertia through the centroid. So once we have the moment of inertia through the centroid, we can use the parallel axis theorem to quickly calculate the moment of inertia about any axis, any parallel axis. Okay, those tables are in the back cover of your textbook. So I'm not sure at College of the Rockies if your final exam is open book or if he's going to give you copies of this table, but either one, you'll have access to this table, which shows for various areas, there's quarter circle, half circle, full circle, semi-parabolic area, trapezoid, arcs of circles, hex-parabolic area, rectangles, triangles, full parabolic area. All of them have formulas for calculating the centroids, which we discussed earlier, and they also have formulas for calculating the moment of inertia on many of them. I don't see a moment of inertia calculation for these parabolic areas. but there are for the circular areas, the half circular areas, the quarter circular areas, the rectangle, and the triangle. On the other side of the cover, there's some three-dimensional shapes, and they have the centroid calculations as well. And they have moments of inertia that we're not going to use because we're only looking at area moments of inertia for this course. But in future courses, you'll want to find the moment of inertia about the x, y, and z axis. So this is the moments of inertia about the x prime, y prime, and z prime axis through the centroid. All right. Once we've calculated the moments of inertia, we can also calculate something called the radius of gyration. And the radius of gyration is found simply by taking the square root of the moment of inertia about the particular axis divided by the area. So this is going to be length units to the fourth. This is going to be length units to the second, which give us length units squared. Take the square root, we end up with a length unit. In terms of the polar radius of gyration, if we have a cylindrical column, then its radius of gyration is just going to be its radius, because all of the particles are located the same distance away from that origin, or from the center of the column. Anything else is going to be different. It's always going to be probably closer than it's going to be closer than the outside of the solid. Again, we're not going to use the radius of gyration in this course, but in future courses you're going to need to calculate it for determining column buckling and other applications. I just can only remember column buckling. So we would, by looking at kx and ky, we'd be able to predict which axis it's going to buckle along, and then you could reinforce it to make sure that the radius of gyration about that axis is the same or greater than the other axis. All right. Let's do an example problem. All right. There's actually two ways of calculating the moment of inertia about any axis. So we're going to do the easy way first, and then we're going to do the hard way. And the reason that you might want to do the hard way is if this particular function turns out to be difficult to integrate using the easy way. So it's usually easiest to integrate with respect to y if we're trying to find the moment of inertia about the x-axis. So this is the moment of inertia about the x-axis. And we would have Ix equals integral y squared dA. So because it's y squared dA, you can tell it's usually going to be easiest to integrate with respect to y in this case, but it's possible to do it both ways. So we're going to solve it twice. So if we're integrating with respect to y, what are my dA's going to look like? Well, whether I'm integrating with respect to x or y, they're both going to be little rectangles. Okay, so what do the rectangles, where would I draw the rectangles on my graph to integrate with respect to y?
In the blue current point up there.
in the blue part, yeah. Are they going to be horizontal or vertical rectangles? They're going to be horizontal, thin horizontal rectangles. So if I'm integrating with respect to y, then this is going to be my dA. And it's going to have thickness dy. And the area is going to be the difference between this line and this line. So this goes to 1 meter. So dA is going to be equal to what? Right, so if we're integrating with respect to y, then I need to write x in terms of y. So x as a function of y would be what? Let's start there. X equals 4th root of y over 2, yep. Y over 2 to the 1/4. So dA is going to equal 1 minus y over 2 to the 1/4. Yep. Okay, just a second. Oh, now I've lost him completely. Oh, there we go. Got it back? Okay. Yep, okay. So our dA is this distance minus this distance. So 1 minus the y over 2 to the 1/4 all times dy. Okay, and if that's my dA, then now I can integrate. So I've got Ix equals integral y squared dA equals the integral, and it's going to be from 0 to 2 meters. Y squared 1 minus y over 2, oops, to the 1/4. dy. Okay, so if we get rid of these brackets, our first term is just going to be y squared. Our second term is going to have a constant part, and the constant is going to be 2 to the negative 1/4, or 1 over 2 to the 1/4, or 1 over the 4th root of 2. I'm going to write it as 2 to the negative 1/4, and then that's going to be y. What's the exponent on y going to be here? I've got y squared times y to the 1/4. Right, it's going to be y to the 2 1/4, or 9 over 4. Okay, this looks ugly, but it's actually not that hard to integrate, right? We've just got a polynomial function with some rational exponents. So the y squared is easy. That's going to go to y cubed over 3. And we've got our constant of 2 to the 1/4. And the y to the 9 over 4 is going to go to right, 4/13 times y to the 13 over 4. We just increase that by 1. And that's evaluated between 0 and 2, but both of these terms are going to be 0 when y equals 0. So we just have to evaluate it at 2. So that's going to be 2 cubed over 3, which is 8 over 3 minus 2 to the 1/4 times, negative 1/4, yep, thanks. 2 to the negative 1/4 4/13 times 2 to the 13 over 4. So the 13 over 4 and the minus 1/4 would bring that to 12 over 4, which is just going to be 3. So 2 to the 3 is 8. Over 3 minus 8 times 4 is 32 over 13. Or you can just plug it into your calculator. .205 or 8 over 39. 205. What are the units? Meters to the 4th. Area moments of inertia or second area moments are always going to be length units to the power 4. Okay, so 0.205 meters to the 4th. And that wasn't really that difficult, even though we had the rational exponents. Let's try integrating with respect to x this time. So if we integrate with respect to x, it's going to be a little bit more challenging. Okay, just a second, let me try and get it back. Oh, no, it's gone again. Got the content? Okay. All right. Yeah. All right. Just let me know if you lose content again, but we're good for now. So if we're integrating with respect to x, this time our rectangles are not going to be thin horizontal rectangles. They're going to be thin vertical rectangles. And that complicates matters because the thin horizontal rectangles were the same distance from the x-axis. Now each one of these rectangles is going to be a different distance from the x-axis. So what we're going to do is we're going to calculate the moment of inertia of the rectangle about its x prime axis or through its centroid, and we're going to use the parallel axis theorem for each one of the little rectangles. All right. right? So this time we're going to have a dA that's going to be the y value times dx. dx is this thickness. But each one of these rectangles is going to contribute towards the moment of inertia by di equals di x prime. So through its centroid, the x prime axis is different for each one of the rectangles, plus parallel axis theorem, y tilde squared dA, and y tilde would be this distance. Now, fortunately, these values aren't that difficult to find. Y tilde, for example, is always going to be halfway to y, because it's the center of a rectangle. So y over 2 is just going to be x to the 4. The moment of inertia of this rectangle about its centroid, we could look up in tables. Right? We'll go to the table here and we'll find the rectangle. Zoom in and hopefully we can actually read it. So the moment of inertia about the x prime axis is 1/12 bh cubed, where b is the width. So in this case, b is going to be dx, and h is the height. And in this case, the height is going to be y. So let's cut that out and put it on our page. Oops. Okay, so there's our rectangle. So that means our di is going to be 1/12 di x prime, 1/12 the base, which is going to be dx, times the height, which is 2x to the 4, squared. Cubed. Thank you. Just seeing if you're paying attention. Okay, so we can simplify this then. So this is going to be 1/12. 2 cubed is 8. X to the 4 cubed is going to be x to the 12th. And then we can combine that with this di. Oh, yep, dx, thanks. So then we have di x is going to be that expression, so 8/12 is 2/3. Should be 2/3 x to the 12 dx plus here we've got y tilde equals y over 2, which is x to the 4th. So x to the 4th squared is going to be x to the 8, and then times dA, which is y dx, which is going to be 2x to the 4th dx. Okay, so we can see we actually end up with like terms here. Both terms have a dx, both terms have an x to the 12th. So we have a 2/3 plus a 2. So it's 2 plus 2/3. That should be 8/3. 8/3 x to the 12 dx. So Ix is going to be the integral from x equals 0 to 1 of 8/3 x to the 12 dx. So we went through quite a bit of work to get to this integral, but the integral is actually easier than the other one. So what's the integral of 8/3 x to the 12? Evaluated between 0 and 1. Ah, they did that without a calculator. Very good. 8/39. And 8/39 is exactly 0.205, or approximately, if this is rounded to 3 sig figs. It's exactly the same as the answer we got before. Right? 0.205, 0.205. Okay, we're going to do one more example with the same shape. This time we're going to determine the moment of inertia about the x prime axis through the centroid. And we could solve that in two different ways, and you can let me know which one you think would be easier. So in either case, we're going to have to find out where the centroid is. So in other words, we're going to have to find y bar. Once we found y bar, we can either take the moment of inertia about our new x prime axis, or we can use the moment of inertia we've already calculated about the x-axis and apply the parallel axis theorem. Which one's going to be easier? Parallel axis theorem could be way easier. The integral of this, where we've got dA's on both sides of the axis, we'd be integrating from y prime equals negative something to y prime equals positive something. It would be uglier. It would be possible, but we've already done the integration about the x-axis. The parallel axis theorem is really easy. All we need to calculate is the area and the centroid, which we need to find either way. All right, so let's first find the area, because we're going to need to find it to find the centroid anyway. Then we're going to find y bar, centroid. And third, apply parallel axis theorem. All right, So if we want to find the area here, which variable should we integrate with respect to? Okay, it doesn't really matter, but it's going to be a lot easier. It's going to be a little easier if we integrate with respect to x instead of y. It's not really that much different either way. So area is going to be the integral between 0 and 1 of y dx. So that's 2x to the 4 dx. Two-fifths. Okay, that was easy. So the area is 2/5. Does that make sense? Seems awfully small. Yeah. Yeah, it's a fourth order polynomial though, and like they've shown it as a parabola, but it isn't a parabola. It's going to be sharper than that. Okay, so if our area is 2/5, then we need to find our y bar. So how are we going to find the y bar? Integral of y dA over a. Okay, to find y bar, is it going to be easier to integrate with respect to x or y? Again, it's probably not that much different either way, but if we're integrating with respect to x, then we need to find, again, the y tilde for each one of these rectangles. And where's y tilde? Halfway up. So y tilde equals y over 2, which just makes that x to the 4th. So that would be the integral of x to the 4th times 2x to the 4th dA all over a. Oh, yep, dx, sorry. So what's the integral of basically 2x to the 8? 2 over 9. And then evaluated between 0 and 1, so it's going to be 2 over 9 divided by 2 over 5. 5 over 9. I'm going to write the step in here. So that's going to be 2 over 9, x to the 9, evaluated between 0 and 1, over 2/5. I should probably write the step in up here as well. So that's going to be 2/5 x to the 5, evaluated between 0 and 1. All right, so we have 5/9 for y bar. Does that make sense? It's a little less than a quarter of the way up. That seems reasonable, given the shape. So then using the parallel axis theorem, parallel axis theorem says I at I x. Those lines that I've been drawing are going to show up on a later page. So it's just one of the little annoyances. I x prime plus y bar squared k. So this is what I'm looking for. This I have, and this I have. So if I solve that for ix prime, which is always going to be the lowest value, the lowest parallel axis, the lowest value of the moment of inertia for any parallel axis is the one through the centroid. So ix prime equals ix minus y bar squared a. So that was 0.205, 0.205 inches to the fourth minus y bar squared. So that's 5/9 squared. Pardon? Oh, it's meters, yep. Five over 9 times my area, which was 2/5. Zero point 0.0817 meters to the fourth. So it's quite a bit lower, and that's because the distances are all less, and the square of the distance is even more less. So it's typically going to be a lot lower. All right. Oops. The next problem is an example of finding the polar moment of inertia. So we're going to find the polar moment of inertia of this semicircle about the z-axis passing through point O. So the polar moment of inertia is J equals integral r squared dA. What shape are my dA's going to be this time? Pardon? Yeah, you probably could do it with little triangles, but then you'd have to look up, you'd have to use the parallel axis theorem, find out what the moment of inertia of the triangle is about its center, and then translate that back to the origin. It'd be much easier to use arcs. So if we use arcs like this, that doesn't really look very good. So this is going to have a thickness of dr. If that has a thickness of dr, And what's its area? Basically, this thin arc we can take and we can straighten it out and turn it into a rectangle. If we turn that arc into a rectangle, it's going to have a width of dr, and it's going to have a length of pi r. Right? The full circle would be 2 pi r, but we only have half a circle. So that would be pi r is the length, and then the width is dr. Pi r dr. You know, is that funny? Okay, so now we can take that and put it in here, and now I'm integrating with respect to r. So this time we're getting it in terms of our outside radius. So we're going to integrate from 0 to this RO. That's r squared times pi r dr. Bring the pi out. Integral of r cubed dr. And what's the integral of r cubed dr? Pi over 4 r to the 4 between 0 and r0. Pi r to the 4 over 4. All right, that was easy. Okay, now we're going to do one that's not quite as easy. Same shape. What's the moment of inertia about the x-axis? What variable do you want to integrate with respect to? If we're finding the moment of inertia about the x-axis, it's usually easiest to integrate with respect to y. So we'll try that first. If we get stuck, then we'll have to use the parallel axis theorem method with the little dA's. So if I'm integrating with respect to y, then I'm going to need to express x as a function of y. So what would x look like as a function of y? Okay. So if that's x as a function of y, then I would have I x equals integral y squared dA. My dA would be x times dy equals rho squared minus y squared all square rooted dy. So this is going to be the integral y squared root rho squared minus y squared dy between y equals 0 and the outer radius. Oh, sorry, y equals negative RO and positive RO. All right, so who knows how to integrate that function? We would use a table. So we'd go to Appendix A, and we'd find in the table And if we didn't have appendix A, then one of the first things that we'd try is to integrate with respect to the other variable. And we're going to find we have something that's equally as ugly. So the table is going to help. So from the table we end up with negative y over 4 RO squared minus y squared, 3 over 2 plus RO squared over 8 y root RO squared minus y squared plus, move that over a bit, RO squared inverse sine y over RO, all evaluated between negative RO and positive RO, which looks really ugly until we start looking at what these limits of integration are and what happens to most of the terms when I put those values in. If I put in y equals either positive or negative RO, what happens to this term? It becomes 0. So it becomes 0 for both limits. What about this part of this term? I still have RO squared minus either negative RO squared or positive RO squared. So that also goes to 0. So what we're left with is RO squared over 8 times RO squared times the inverse sine of y over RO that's all constants on the outside between negative RO and RO. So that's going to be RO squared over 8, so RO to the 4 over 8. And what's the inverse sine of well, first one's going to be negative 1. What's the inverse sine of negative 1? Or negative pi over 2? Yeah, 3 pi over 2 would work as well. And what's the inverse sine of positive 1? So we're going to have pi over 2 minus, we have to use the negative pi over 2, minus negative pi over 2. 2 pi over 2. So that's just pi. No, it's pi over 2 minus negative pi over 2. Okay, so that's our IX. I can also write that more simply, pi RO to the 4 over 8. No. Nope, because when we calculate it at RO, it's pi over 2. When we calculate it at negative RO, it's negative pi over 2. So we have the pi over 2 minus negative pi over 2 gives us just pi. So pi r o, or outside radius, over 8 is the answer. We're not asked for it, but what's IY? We don't have to integrate to find it. Oh, it's the same as that. A good guess would be that it's half of that, because it's half the distances, but there's twice as much area. The reason we know it's the same is because j is equal to ix plus iy. So iy is equal to j minus ix. So that's pi ro to the fourth over 4 minus pi ro to the fourth over 8 equals pi ro to the fourth over 4. Now we went to the trouble of doing the integrals on this one, which is good practice. Over 8, yeah, sorry. This is one of the areas that's actually covered in the back cover. So if we have a semicircular area like this, then its moment of inertia about the x-axis is 1/8 pi r to the fourth, and about the y-axis is 1/8 pi r to the fourth, which is what we calculated, which is good. This is one of the ones where this isn't a prime, so this isn't about the centroid. So to find the moment of inertia about its centroid, we'd first have to find x bar, or in this case it's y bar, but we have a formula for that, and then we can use the parallel axis theorem.
Will we generally be able to find the table value for the integral no matter what variable here?
So the question was, will we be able to find a table value regardless of which, an integral in the integral tables?
Yeah.
Not necessarily. Only if it matches one of the patterns that's there. So there's quite a few common patterns that come up. Sometimes it doesn't work. So you're going to have to use substitution or some other integration technique. Any problem that I'm going to give you on the exam is solvable without using the integration tables or anything too complicated. On the assignment, you should be able to figure it out, because then you've got the time to look it up in the tables, and you've got the time to try substitution or integration by parts or whatever other method is appropriate.
So we don't really have to worry about it.
Don't worry too much. The integrals will all be, on the final exam, the integrals will all be things that you can complete in a reasonably short amount of time. And there's not going to be a lot of integration on the final exam either, because it's only a small part of what we're doing in the statics course. All right, so that's the last integration that we're going to do in this chapter, well, that we're going to do in class. The next section talks about situations that arise much more commonly, and that's finding the moment of inertia of a composite part. So something like this I-beam, rather than using integration over this discontinuous function to find the moment of inertia, we'd use composite parts. So similar to finding the centroid. Using a sketch, we identify the composite parts. So we draw a line, for example, here, and here, and then we'd have 3 different rectangles. Identify the composite parts and indicate the perpendicular distance from the centroid to the reference axis. And we're doing that because we're going to have to apply the parallel axis theorem. For common shapes, use moments of inertia about centroid given in the back cover of your text. So that's the page we were looking at. So any rectangles, triangles, half circles, circles, The formulas are all in the back. And then we apply the parallel axis theorem. For each part whose centroid is not on the reference axis, use the parallel axis theorem to determine the moment of inertia. Sum all of the moments of inertia for each of the composite parts. If the part is a whole, then it has a negative moment of inertia, so we would subtract it. So it sounds as easy as the centroid calculations, but there are quite a few more steps. So we're going to do an example here. So this is a beam. It's like a box beam, hollow box beam. So we've got these two vertical pieces of wood, and they're held parallel by two horizontal pieces of wood. So how would you like to divide these pieces? How would you like to section it? Yeah, basically the pieces of lumber, each one's going to be a section. So we can call the left and right ones 1 and 2, or A and B, or whatever we want to call them, and we'll call this 2 horizontal boards 3 and 4. All right. So I'm going to organize this data in a table. And I recommend that you do the same because there's a lot of data. So for each of the sections, we're going to have to calculate the area because we're going to be applying the parallel axis theorem. We're going to have to find its centroid. So it's x bar and it's y bar. We're going to calculate the moment of inertia of the shape about its own centroid. So I bar x prime I bar y prime. And then we're going to apply the parallel axis theorem to find Ix and Iy. Okay, so we'll start with section 1. So section 1 is this board, and it is 15 millimeters thick, and 150 and 50 and 100, so 300 millimeters deep. So 300 by 15. (4,500 millimeters squared). I could use meters instead of millimeters. The only difference is instead of getting ridiculously large numbers, when we start taking them to the power 4, we'd end up with ridiculously small numbers when we take them to the power 4. So it doesn't really matter, as long as you keep track of your units. What's x bar going to be? And the centroid is right here. 7.5 from where? Right? Here's our y-axis. So it's going to be the 60 plus half of the 15. So negative 67.5 millimeters. I'm going to save myself some time here. These are all going to be in millimeters squared. These are all going to be in millimeters. These are all going to be in millimeters to the fourth, all the way over. Okay, what's y bar? 0. Right? The x and y axis go through the center of the beam because we're basically interested in the moment of inertia about the centroid axis of the composite beam. So that's going to be 0 for the y bar. All right, and now we need to find the moment of inertia about the centroid of this piece. So we would look that up. And for all of these, because they're all rectangles, they're all going to be 1/12 BH cubed for the moment of inertia about the x prime axis. For the moment of inertia about the y prime axis, it's going to be 1/12 b cubed h. B is the width, so in this case the width is the 15 and h is the height, so in this case the height is 300. 3.375 times 10 to the 7 millimeters to the fourth. And now I can jump ahead. What's the moment of inertia about the centroid of the composite going to be about the x-axis? It's going to be the same because they have the same x-axis. Y bar 0. All right, moment of inertia about the y prime axis. It's going to be 1/12 b cubed, so 15 cubed times h, which is 300. Okay, so 8.4375 times 10 to the 4. Okay, and this time it's going to be different when I take it about the centroid axis. So we're going to have to add to this x bar squared, so 67.5 squared times the area. Okay, so it actually ends up being not that far off of the IX, even though we were like 3 orders of magnitude smaller when we were taking it about its own centroid. That's because it's thin along the in the x direction. So its moment of inertia about the y-axis, about its own y-axis, is small, but as I move it away from the y-axis, it gets bigger. Okay, second one is going to be very easy. Second one is the other side, so its area is going to be the same. Its x bar isn't the same, but it's the same magnitude in the opposite direction. So it would be plus 67.5. Y bar is the same, which means all of these other values are going to be the same because the x bar gets squared anyway. So 3.375 times 10 to the 7 8.4375 10 to the 4, 3.375 10 to the 7, 2.059 times 10 to the 7.
What was the height and the base of
So on these ones, so the base is still the base, so the width, so that's the 15 millimeters for this piece, and the height is the distance on the y-axis. So the only difference between this one is which variable gets cubed. So it's always the opposite of the variable we're taking about, or the axis that we're taking the moment about. So moment about the x-axis, it's the y value that's cubed, because it's the distance from the x-axis that's important, which is the y value. Same thing on IY, it's the x value that's cubed. All right, and now we move on to 3 and 4. So 3 is this piece of wood, which looks like it's 120 by 15. So 120 by 15 1800 millimeters squared. The x bar is 0 because its centroid is right here, so it coincides with the y-axis for the composite. But its y bar is not 0. Its y bar is, right, this 50 millimeters to the center. And it's going to be plus 50. Oops. So we would calculate the 1/12 base times height cubed. This time the base is 120 and the height is 15. It's going to be a lot smaller. 3.375 times 10 to the 3. Okay. Must be a mistake then. 10 to the 4. All right. And then that's not going to be the same. So if we apply the parallel axis theorem to that, we would add y bar, which is 50 squared times 1800. Okay, that agrees with what I've got. And then moment of inertia about the y prime axis, that's the 1/12 b cubed h. So b is 120, h is 15.
2.16 times 10%.
That's what I've got, 2.16, exactly, 2.160?
Yep.
Yep. Times 10 to the 6. And then, since it has the same axis, 2.16 times 10 to the 6. And we finally get to part 4. Part 4 is the same area, same x bar, opposite y bar, same values for all of the moments of inertia. All right, so I put ditto marks in here, but I wrote them in here because these are the ones we're going to add up. So my composite beam, we're just going to add up all of the IXs and IYs. So IX,
7.657.
okay, 7 points, rounding to 3 sig figs, 7.66 times 10 to the 7. And that's going to be millimeters to the fourth, same as what we've got above. And IY,
4.55 times.
that's what I've got as well, 4.55 times 10 to the 7 millimeters to the fourth. All right. So this problem has a T-shaped beam, and we're asked to calculate the moments of inertia about the beam's cross section. So second area moment about the x prime axis, the x-axis, and the y-axis. So the x prime axis is going to go through the centroid as shown. So if I want to find the moment of inertia about the x prime axis, I need to find out what this value of y bar is first. So that's going to be my first step. Anybody guess why they're asking about the x prime axis but not the y prime axis? Right. The y prime axis is the same as the y axis because it's symmetric about the y axis. It's not symmetric about the x axis. So how are we going to find y bar? Okay, but are we really going to integrate for a shape like this? Right, so we're going to do it by sections as well. So if we divide it into two sections, let's call the top one 1 and the bottom one 2. So we would find y bar equals the sum of the y tilde times the area over the sum of the area. So if we create a little table here that's got our section, our area, our y tilde, and y tilde times the area, and that should help. So section 1, what's my area? 30,000 millimeters squared. What's my y tilde? Nope. Remember, the y tilde is the distance from the x-axis. So we have 100 and then half of the 300, so it's 250. And we multiply those together to get y tilde times the area. That's going to be millimeters cubed.
7.5 times 26.
Okay, and then we look at our second section. Second section has an area of 100 times 200, 20,000. And it has a y tilde of half of the 100, or 50. $1 million, 1.0 times 10 to the 6. So if we add those up, 8.5 times 10 to the 6. Add these up, 50,000. So y bar then is going to be 8.5 times 10 to the 6 millimeters cubed over 50,000 millimeters squared. 170 millimeters. All right. Now what? Right, now we're going to need a much bigger table for calculating our moments of inertia. So the bigger table is going to have each section. What's our time? Oh, actually, we are out of time. So we'll finish this one up next class, and we're almost finished the material. So we'll finish up, and then we'll start a bit of a review for the final exam. So I'm going to start by reviewing the material we've done since the midterm, and then possibly on Thursday's class we'll go back and review the pre-midterm material. Most of the final exam, 2/3 of the material on the final exam here is going to be pre-midterm or post-midterm, and 1/3 pre-midterm. College of the Rockies, I think you guys do like 3 different midterm exams and a final. Yeah, so the weighting of the material is probably going to be different for you guys for your final exam.
We have 6 questions.
So we're not doing a final exam?
You are going to have a final exam, yes. Jim will be giving you your exam. So it'll be different than our exam. Same material. But because these guys have only done 1 midterm exam, the weighting will be a little bit different.
In the beginning, like at the midterm, so there's going to be 6 questions on the final.
6 multi-part questions, each of which should take approximately half an hour. Some more, some less.